lossless data compression. This is a direct coding using geometric series. Now we wish to code a number which is from m equal to 2 power L dash is a value with an s equal to 2 power L, where L dash is significantly much larger than L, and we wish to code it losslessly. Let L dash by L is equal to C, where C is the compression ratio. Now for the L dash bits of information that needs to be coded in L bits. Now we know that the ratios associated are 1 by 2, 1 by 4 and so on for the individual bits from the leftmost bit to the rightmost bit. Up to the last value is 1 by 2 power L dash. Now these are the ratios for those L dash bits. Now if we wish to code them in L bits, then we would require the following. The ratio for the 0th bit or the rightmost bit should be close to 1 by 2 power L dash itself, and then we require the ratio for the L dash minus 1th bit for the L minus 1th bit, for the L minus 1th bit must be nearly equal to half itself, and also more importantly, sum of the lower order bits must add up to close to the next higher order bit only. So these are the conditions that must be satisfied if you wish to assign ratios to the L bits which satisfy these three. Now initially on first looking at it, on first sight or on first look, it doesn't seem like it is possible, but actually if we examine it even more closely, it is actually very much possible, more or less possible. If we assign to the ith of the L bits there 0, 1, 2 and so on up to L minus 1, if for these L bits, if we assign the ratio 1 by 2 power L dash plus 1 minus C into I plus, in general for the ith bit, if we assign this ratio there to the ith bit, I from 0 to L minus 1, then it will more or less satisfy all the conditions that we require. We can check this out. If I is equal to L minus 1, since L dash by L is equal to C, where C is this, the ratio of L dash by L, the leftmost bit value will come to half, the rightmost bit value will come to 2 power L dash minus C, which is very small. We can also see that the ratio, this is a geometric progression whose common ratio is R is equal to, you can check it out, it is 2 power C, whose first term is again 1 by 2 power L dash plus 1 minus C, and sum to I terms will be very close to 1 by 2 power L dash plus 1 minus I plus 1 into C, which is nothing but the next higher order term. In other words, the ratios will also, the least ratio will be as small as we as it possibly can be. Largest ratio will be very close to half itself, and some of the ratios will more or less add up to the next higher order ratio itself. So all these conditions will be satisfied by just these assigning these ratios to these L bits. So L dash bits can be coded more or less fairly well in L dash L bits. The ideal way to ratio for L dash to L again will be close to L itself. In other words, L must be close to square root of L dash. We can suppose that we will not be too far from the truth to getting an optimal coding. So in a few iterations you should be able to code L dash bits in L bits perfectly. So this is just an illustration of the fact that what appears to be initially seemingly true of something on its surface and what is actually in fact true on it if you examine it in its depths are often two different things. What seems impossible initially on first look is actually very much possible if we look at it more carefully and closely.